one of you, and who is not here, wanted me to discuss why supersymmetry. So that's what I decided to do today. But then he is not here. Should we do that? Or should we discuss supersymmetry breaking? I don't know if, did you get these lecture notes of my Bangalore school lectures? Did everybody get that? I have a few copies of that here. So if anyone has not gotten it, you can take this one. Did you get it? Huh? Yes. And then there is also an old paper of mine here. There are some copies of that. This paper discusses why supersymmetry. You have a copy of this. This is Pramana paper. So we'll discuss why SUSY. This is another set of papers. You taken that? So the question we ask is that why do we expect a fundamental symmetry relating fermions to bosons to be a property of nature. There's an extraordinary reason for us to believe that such a symmetry of nature has to be there. But before I go over to that, let me summarize what we know about present-day particle physics. What is our understanding of present-day physics of elementary particles and forces experienced by them. This is an understanding which has been developed over a long period, developed over more than 1.5 centuries, starting from Maxwell's theory. And this understanding is made up of some dogmas or guiding principles. One of them is what you know, that every interaction fundamental interaction is governed by a gauge principle. So electromagnetism is the oldest example of a gauge theory, and more complicated electroweak interactions are governed by a gauge theory based on gauge group SU2 cross U1, SU2 left cross U1 hypercharge. And this symmetry is broken through spontaneous symmetry breakdown. Spontaneous symmetry breaking leads to U1 electromagnetic theory. And this spontaneous symmetry breaking is done through a scalar field, elementary scalar field. The so-called Higgs doublet. And after the symmetry is broken, we are left with a physical field, which is the Higgs field, which is what everybody is hunting for right now. And hopefully, we may have already seen it in LHC with mass. This results into a physical field called Higgs field, Higgs particle, with mass of 121 GeV, if very likely if the experimental results, initial experimental results of LHC are confirmed. Something of that kind. Then strong interactions are also governed by a gauge theory of group, gauge group SU3. So you have electromagnetic interactions, weak interactions, and strong interactions. These are the three interactions that elementary particles experience. All of them are governed by gauge theories. So this is maybe B, and this is A. And C, even gravity may be viewed as a gauge theory. We don't understand quantum theory of gravity very well, but very likely that's also a gauge theory. With this gauge particle, like for electromagnetism, we have a photon. Weak interactions, we have W plus and W minus and Z gauge boson. For strong interactions, we have the gluons, 8 gluons. Here, the corresponding gauge field would be spin 2 graviton. That's one principle, the gauge principle. Second principle, that is that every interaction except gravity is described by a renormalizable field theory. Renormalizable gauge field theory. So standard model of electroweak theory, Glashow-Salam-Weinberg model, which is a gauge theory of SU2 cross U1, is a renormalizable gauge theory. The strong interaction gauge theory, QCD, based on SU3 color gauge group, is a renormalizable gauge theory. Gravity is only one theory that we don't understand well enough. Quantum theory of gravity we don't understand well enough. So we don't know how to describe that. But very likely, a quantum theory of gravity would be a finite theory. Unlike these theories, which are renormalizable, which means they have infinities, and we have a systematic method of handling those infinities, understanding how to deal with them. Theory of gravity may be one that would have no such infinite divergences, but would be finite. But that's still an open question. There are candidates for this theory. The string theory is one candidate. There are other candidates for this theory, but we don't understand it well enough. So, but it's a good question. The principle of renormalizability is essentially a statement that a given theory is valid up to a certain energy scale. And we don't know how the physics of that energy scales larger than that would affect the theory. Say if I'm doing electroweak theory, and if I'm doing it up to 100 GeV, that's fine, but that's because what the characteristic scale of electroweak theory is. Gauge boson is 100 GeV mass. But the particles that are involved in electroweak theory could also have interactions which are governed by energy scales larger than that. They could be heavy particles larger than that. There is, in fact, gravitational interaction, which is characteristic scale. Quantum gravity is the Planck scale. Planck scale is very high. So there could be physics beyond the scale to which a particular theory is applicable. So it is the ignorance of how the higher energy effects will affect the lower energy theory, which is reflected in emergence of divergences. So what we say is that our ignorance of high energy properties of a certain physical system, if it is of the kind that you can reabsorb in defining a finite set of the parameters of the low energy theory, then such a description would be renormalizable. Right? So you expect any theory which for some reason you think that there is some physics beyond the energy scale that is relevant, if at all that description has to be meaningful, to be renormalizable. But quantum theory of gravity is a theory which has a characteristic scale of Planck length or Planck momentum from Planck energy. And in nature we think that there is no scale beyond that, because we think that's the ultimate scale. If that is the ultimate scale, there is no physics beyond that. If there is no physics beyond that, there is no more ignorance that we have to hide in terms of renormalizability. So then a quantum theory of gravity better be finite. Because if it's not finite, then that will tell us that there is some scale which is some physics beyond the Planck scale. So if Planck scale is the ultimate scale, then the description of such a theory has to be such that there are no divergences. So that's why one suspects that a good quantum theory of gravity would be finite. Yes, but that would be in tune with how we understand physics. If that doesn't happen, if it is renormalizable, that would suggest that there is a scale beyond Planck's scale which we don't understand. Okay? So that's the reason why, but theory of quantum gravity is not our concern right now. Huh? Then there is another dogma. Whereas these two dogmas are well founded in the sense that we already know electroweak and strong interactions can be described according to these two principles, the gauge principle and the renormalizability. There's a third principle which we don't know whether that is right or not, but that for some reason, for reasons of aesthetics, for reasons of simplicity, we think that that should also be there. And that is unification. Unification of all fundamental forces. In fact, we have seen some examples of unification because that's what helps us build this intuition that it must be true for all of them. For the electromagnetic, unification was Maxwell's theory. Electric forces and magnetic forces got described in one framework, and that was Maxwell's electromagnetic theory. Electromagnetic forces and weak interactions got described in one framework, which is Glashow-Salam-Weinberg model. It's one framework but it's more like a mixed framework because there are two coupling constants there. One is electroweak coupling constant, the weak coupling constant there, and one is electromagnetic coupling constant. But there is some combined description. So this experience suggests that presumably all these theories, electromagnetic, strong, electroweak and strong forces may be described by one theory. So that is a guiding principle, but not compelling. We don't have any evidence for it as yet. Okay? So unification. So for example, electroweak and strong interactions, that's QCD, which is SU2 cross, this is SU2 cross U1, and this is SU3, color left and hypercharge. These forces can be put into one framework, which is again a renormalizable gauge theory. Can be unified. There are several ways of unifying them, but one way of unifying them is, for example, it can be unified into a gauge theory based on SU5 gauge. There are other examples. Even SO10 is another example. SO10 is another example. So in this worldview, if this is so, then this theory would be valid at some high scale, energy scale, where it would break into these, and then these would break into U1 electromagnetic at 100 GeV, which is standard electroweak theory. So in this picture, SU5 would break into SU3 color cross SU2 cross U1 at some scale mu, call it grand unified, mu gut, and that turns out to be of the order of 10 to the minus 16 GeV. 16, 17, some large number. And we know how to break gauge symmetries. We have experience with electroweak theory how to break gauge symmetries. We break them through elementary scalar fields by giving them vacuum expectation value. Choose an appropriate potential So that picks up a vacuum expectation value, and that vacuum expectation value breaks the gauge symmetry. So this is also done through an appropriate scalar field of this SU5 theory, which picks up a vacuum expectation value, which is characterized by this scale, and then you get this. And then subsequently, you break it at weak scale of 100 GeV, and you get SU3 color cross U1 electromagnetic. Now, the important thing to realize is that the two scales at which govern the physics of this picture is 100 GeV of electroweak theory and 10 to the 16 or that large for grand unified theory breaking into the Stendhal model. And they are vastly different. The 14 orders of magnitude different. And this is done through scalar fields, this is done through scalar fields. Vacuum expectation value of scalar fields here, vacuum expectation value of scalar fields here. Of course, some people think that this is also an indication that even gravity should be unified. Quantum gravity should also be unified in this picture. And that is so because if you look at 10 to the 16 GeV, the scale of quantum gravity, is the Planck scale, and that is 10 to the power 19 GeV. That's only 3 orders of magnitude away from this scale. So some people would like to think that presumably, since the two scales are not that far away, even gravity should be. So there may be one picture of describing all the fundamental forces of nature: gravity, strong interactions, which is QCD, and electroweak interaction, which is Glashow-Weinberg model. And that's what string theory does. But for our purpose, what it is to notice that this is done through elementary scalar fields. There is another principle that guides our physics, the fourth principle or fourth dogma of high energy physics, that's called naturalness. Naturalness is a very technical term in this context. Naturalness, what does a naturalness mean? Naturalness means that any small parameter in a theory, small compared to others, should be a reflection of an approximate symmetry. That's the principle of naturalness. The principle of naturalness is that any parameter in a theory should be a reflection of an approximate symmetry. So if that parameter is 0, then symmetry becomes exact. And when it has a small value, that symmetry is approximately broken. And this principle is one which creates problem for elementary scalar fields. Elementary scalar fields create tension for this principle. Generically, So what we'll do is that we'll discuss this dogma of naturalness in detail now. So naturalist dogma. What we'll ask is, we'll ask particularly the question is that the scale of electroweak theory is 100 GeV. Is it a natural parameter? Is scale of electroweak symmetry breaking a natural parameter? It's 100 GeV as compared to 10 to the 16 of grand unification, or it's 100 GeV as compared to 10 to the 19 GeV of Planck scale. So it's a small scale. But is it natural, or in other words, is the vacuum expectation value of Higgs field in standard model of electroweak theory, standard model of electroweak theory natural? Because it's this vacuum expectation value of the standard model Higgs which governs the electroweak theory symmetry breaking scale. And that's also an object which gives the mass to the physical Higgs field. So an equivalent question is the mass of Higgs field or Higgs particle a natural parameter? And what do we mean by natural parameter here? Is there any symmetry associated with it? And if there is no symmetry associated with it, the other way of formulating the same question is that is the mass or mass of the Higgs particle, let me call it mh, is mh stable under radiative corrections? That's an equivalent way of asking this question. Because if there is no symmetry associated with it, then it cannot be radiatively stable, which means quantum corrections would be large for such an object. And we'll see how that happens. But before we go to that, let's first understand some examples of what are examples of natural parameters. So some examples of natural parameters. So let's start with QED. QED, quantum electrodynamics. All parameters of this theory are natural. Now, how do we describe QED? QED is described by Lagrangian density for photon field f mu nu square coupled to some charge fermions. Let me call lambda fermion f. F is 1, 2, 3 electron, muon, quarks, up quark, down quark, all charged particle fermions. I gamma mu d mu minus I e q f a mu minus m f lambda f. So, sum over f. F could be electron, muon or quarks, up and down, whatever quarks. So, that is what is QED, described by this Lagrangian density. And E is the electromagnetic coupling, Qf is the charge of the fermion lambda f, this is a number, minus 1 for electron, plus 1 for positron, so on and so forth. And then mass of the fermion, mf. So, this theory has two parameters, mass of the fermion and electromagnetic coupling, two parameters. Mass of the fermion and two sets of parameters. For every fermion there you have one mass, two sets or two sets. The masses of the fermions and electromagnetic coupling. Qf is a fixed charge, so that is a number. Okay. So, now question is, are these natural parameters? We have claimed that they are natural parameters. What does that mean? That means there must be some approximate symmetry associated with them. Now, what is the symmetry associated with them? So, if I take mf to be 0, that leads to a symmetry which is chiral symmetry. Massless fermions have chiral symmetry. Chiral symmetry is separate conservation of the left-handed fermion number and fermion and separate conservation of the right-handed fermions. How do I see it? Now, this mass term that I have written here, let me write it for electron, mass term for an electron. Mass term for electron is m electron lambda e bar, E is electron, right. I can rewrite this as m e left-handed bar lambda e right-handed plus lambda e right-handed bar lambda e left-handed. This breakup everybody knows how to do it. Put 1 plus gamma 5 and 1 minus gamma 5 by 2 and make the projections. And the kinetic energy term for electron is lambda d slash lambda, or d cap covariant derivative including this slash lambda. This I can write as lambda bar d slash lambda plus lambda r d slash lambda r. The left and right projections. Now, this is a term which talks to left with left and right with right, whereas this is a term which mixes left and right. So if m is 0, there is no mixing of left and right. So that gives you separate conservation of left-handed fermions and right-handed. Separate conservation. Of left and right fermions. So MF is M electron is a natural parameter. And what is the consequence of it? Consequence of its being natural? If I start doing quantum perturbative quantum theory with this electrodynamics and try to find out what is the possible correction that electron mass can have due to radiative, let's say, one loop corrections, quantum corrections. So, quantum correction of an electron mass, delta m square, that will come from a one loop diagram, is that you have an electron and you have electromagnetic field going on. This is the kind of a diagram. From this diagram, you will calculate what is the correction to electron mass. And if you did this calculation, what would be the answer? Answer turns out to be, if you remember it, m square times E is the electromagnetic coupling, E times E is E square is alpha, right? Electromagnetic structure constant is alpha is E squared divided by H cross C, some 2 pi or 4 pi's. So it's proportional to ME square, it's proportional to alpha, and it's proportional to some divergence, because it's a log divergent. So delta m square is me square alpha times me square log lambda square. At one loop and higher loop, similar results, alpha square, alpha cube. Now, if m square is 0, in the limit m square 0, this correction goes to 0. So this is an example of that the radiative correction to the electron mass is proportional to electron mass itself. So it's as small as electron mass or smaller. It cannot be large because of alpha even large, smaller. So the radiative corrections are small. They don't destabilize the mass of the electron. This is what is the property of a natural parameter. A natural parameter will be one with which there is an approximate symmetry, and that approximate symmetry is essentially responsible for making sure that the quantum corrections to that parameter are also small. Soon we'll see an example when the results map. So electron mass is a completely natural parameter. So are other fermion masses in QED. Now what about the other parameter, electromagnetic coupling? Electromagnetic coupling is also a natural parameter. Why is it a natural parameter? Electromagnetic coupling E is also a natural parameter. And that's because if E goes to 0, interaction goes to 0. And interaction goes to 0 is the highest possible symmetry, because it means in the interactions the fermion number is not unchanged, photon number is not unchanged, because there is no vertex that can convert. It doesn't allow a fermion to emit a photon. So fermion is always a fermion. It cannot emit a photon and become a state with a fermion plus photon. So a coupling becoming 0 is the highest possible symmetry. It's a trivial symmetry. Is because this would mean conservation of, this is conservation of any type of fields, electron or any type of particles. Electrons are always electrons. They don't become electron and a photon. So electron number, that every type of number is always concerned. No photon emits an electron and a positron, because that would mean an electron number getting converted, a photon number getting converted into an electron positron to fermion number. So there is no such interactions. So coupling constant going to 0 is a conservation of the theory. Particle number, so the particle number of any type is conserved, or conservation of the particle number of any type. Now what does this mean for hereditary corrections? This property is the basic property which has the consequence that if I were to calculate correction to electromagnetic coupling, radiative correction to electromagnetic coupling, say one loop correction, where would it come from? It would come from a diagram of the kind: electron emitting a photon, that is strength electromagnetic, electron emitting a photon and becoming a positron, or electron positron radiating and becoming a photon, and then you put a photon line here. So that would be, for example, a one loop correction to electromagnetic coupling. Now if you calculate this in QED, what does this correction look like? This coupling is strength E, this coupling is strength E, so this is E, this is E, the total strength is order E cube. So that we should simply just let me write it E cube. And then there are, see, there's gamma mu here, gamma and alpha beta gamma, gammas hanging around, some other structure. And then there is this loop integration, which is log divergent. Lambda is the cutoff for divergence. Capital lambda is the cutoff. the same lambda that I put here. So which means the correction to the coupling is proportional to coupling cube. So if E is 0, this is 0. I cannot radially generate a coupling, electromagnetic coupling, if I started with it to be 0 at the tree level. So it would be small. Radiative corrections to electromagnetic coupling are small because they are order E cube. So radiative corrections are small and proportional to E cube. So QED is a perfectly natural theory, and radiative corrections to various natural parameters are small in QED. By small, we mean they are divergent. See, log divergence is a large number. Huh? But what we mean is that they are small after you have regularized it in some particular way because of this factor. And if E is 0, this is 0, irrespective of what log, how do you regularize it. And we'll soon see an example where this doesn't happen. Okay, that was QED. Second example, QCD. QCD is a perfectly natural theory. Again, how do you describe QCD? QCD is described by Lagrangian density of the SU3 gauge fields. A runs from 1 to 8. F square with SU2 group index A runs from 1 to 8, 8 gluons, and then you have quarks. So let me call it lambda I, gamma mu, delta ij, d mu, minus I by 2 G dA Ij A . So let me think of one quark. I have many quarks up, I have many color triplets. Each quark is in up quark is in a triplet, down quark is in a color triplet. So color triplet is given by I, index I. I is 1 to 3. So this is the gauge coupling. G is the SU3 gauge coupling. And M is the mass of the quark. So this is what describes the QCD for one color triplet. And if you have many color triplets, you write for each one of them term of this kind and sum over that. Now this is more like exactly like QED. What do we have? We have two parameters here again. The quark mass M and gauge coupling G. and quark mass coupling, radiative correction say one loop correction. For this is given by the same kind of a diagram that we wrote for QED, except that this is a gluon now. Fermion, lambda, lambda, and this is a gluon. And this would again be given by the same kind of a law, proportional to the quark mass times the coupling constant times Coriolis divergence and some numerical coefficients. So like the electron mass of QCD, this is also correction to mass is proportional to m square. So if m square is 0, this correction goes away. So like in QED, what we have is that m going to 0 is a chiral symmetry. So this parameter going to 0, there is an enhancement of the symmetry. There is an exact symmetry, which is the chiral symmetry. And this mass is a reflection, presence of this mass is a reflection of that symmetry being broken approximately. And under radiative corrections, this number is stable, which means it does not pick up any large corrections. It picks up corrections proportional to m. Similarly for couplings, same as the QED coupling. And a coupling, if you want to do the same kind of a diagram, would be except for the extra structure of there being group indices in various places, which will give you some different numbers, this object is again proportional to G cube. So the same remarks that were applicable to electromagnetic coupling are applicable here. Radiative corrections are small, proportional to G cube. And if G is 0, they disappear. And G going to 0, like we said, it means no interactions, and no interaction is the highest symmetry, because that conserves the particle number of each type in any interaction. So what we have learned in these two examples is that any theory that is made up of pure gauge fields and fermions contains only natural parameters. Okay. Any theory made for gauge fields and fermions contains only natural parameters. Is that clear? That's the lesson of this discussion. Moral of this discussion is that any theory which is made up of only fermions in gauge fields contains parameters which are natural, and therefore such a theories are natural. Now let's go over and see what happens to a theory which contains an elementary scalar field. That's what standard model has. Standard model of electroweak theory has an elementary scalar field. elementary scalar field. So quantum theories containing elementary scalar fields are not natural. How do we see it? Consider a theory of a scalar field the kinetic energy of the scalar field half d mu phi minus m square phi square by 2 minus lambda factor phi 4. Now we have two parameters here. The mass and the coupling lambda. Now let me ask the question, if I take mass to be 0, is there a symmetry in this theory? M to 0, you have no this term. Then this Lagrangian, does this Lagrangian have any symmetry? Does anybody know? Theory of massless scalar fields has some symmetry. Theory of massless fields has some symmetry. Yes, there is some symmetry, which is scale invariance. But if you recall, at some stage, we did when we were doing gauge theories, and we did one loop corrections to coupling constants, and then that theory classically also was gauge invariant because we did pure gauge theory with no masses in it. So it had a scale invariant. But then we discussed, if you remember, at quantum level, scale invariance was broken. Do you remember? In one of the classes I discussed, I showed that scale invariance at the one loop level in QED, in Yang-Mills theory, pure Yang-Mills theory I discussed, is broken. And scale invariance was proportional to, non-invariance was proportional to exactly the beta function of the coupling. If you don't remember it, go back to your notes and check on that. And that statement is that classically, when I put m equal to 0, I do have a scale invariance, but this scale invariance is not respected by quantum effects. So quantum effects break scale invariance. Which means this invariance would be broken radiatively. And there is a very simple way to expect that why quantum effects should break scale invariance. I said a theory which has a mass dimension parameter cannot be scale invariant. But when I do quantum corrections to a theory with no mass parameter in it, classically no mass parameter in it, I have divergences. Divergences means I have to introduce a cutoff. Cutoff is dimensionful. Or I have to use a normalization if I am doing dimensional regularization, that mu. Remember, there is some scale mu you put in there. So there is a dimensionful scale that you put in there. So you cannot be doing radiative corrections without introducing a scale with mass dimensions, a parameter with mass dimensions. So the moment you introduce that, your scale invariance is broken, because general principle of that theory, which has a parameter of dimension mass in it, cannot be scale invariant. So radiatively, scale invariance is always broken if you had a theory classically which had scale invariance, and that is due to the fact that you have divergences in the theory. Divergences generically make scale non-invariance. Is that clear? Huh? That is that's mass term, but scale invariance. Scale invariance was, if you go back to, for example, QED in the gauge theory example that we did it, scale invariance came because coupling constant became scale dependent, right? Coupling constant becomes scale independent in quantum field theories. Huh? So the scale invariance, non-invariance came from there. Constant becomes scale invariant. They become scale dependent.
But how that is the mass?
Because when it becomes scale dependent means scale is mass, right? Some energy mass, right? So dimensionful object, right? So quantum effects break scale invariance. So then in this theory, m equal going to 0 is not really a quantum symmetry. So there is no symmetry, no quantum symmetry for m going to 0 limit. Hence, the mass of a scalar field cannot be a natural parameter. Of an elementary scalar field cannot be a natural parameter. What does it mean for the radiative correction of mass? See, earlier we saw that all the examples of natural parameters that we had, their radiative correction was proportional to that parameter itself and was small. What happens to this theory? Now let's calculate radiative correction to the mass. Radiative correction. I hope by now you used to the term radiative correction means quantum correction, perturbative quantum correction. Radiative correction to mass. Now, this is the correction. Where will it come from? It will come from a diagram of the kind, you have scalar field here, you have a loop because of this interaction. This interaction is strength lambda, and you have a diagram of this kind, external lines scalar field phi and a 1 phi loop. This is the kind of a diagram that will give you the correction to the scalar mass. you simply put external momenta on these lines to be 0, that is directly the mass correction. Now, if when the external momenta are 0, let me put the loop momenta in this loop to be k. So, then what is this correction like? Coupling constant lambda times this propagator 1 by k square minus m square d4k. That is what it is, up to some numerical constants. And if I have written a propagator in Euclidean metric, because that is what is k square minus m square, right? Scalar field propagator. Let me write it again. Okay. Lambda d4k. This is what this is. One by k square minus m square is the propagator, and I am putting external momenta to be 0. So, the internal momentum is all that is there in the propagator. Otherwise also, if I put external momentum also, does not matter, because internal momentum that will go through here, right? Yeah. So, this is what it is. Or I can rewrite this as lambda k square minus m square. Well, d4k is dk times some angular integration. Angular integration is some numbers, because nothing depends on that, so I take it out. So, this is dk square, k square divided by k square minus m square. Now, this object, if you calculate it, clearly for large k, this is like 1, this is integral dk square, which means this is lambda times this capital lambda cut off square. This is quadratically divergent. So, if I integrate up to lambda square, this is what my answer is. Is that clear? So, in this theory, if I were to calculate the correction, one loop correction to the scalar mass, it would be, let me write it here again. So, it is a quadratically divergent integral, and therefore, the answer would be proportional to lambda square cut off square. Now, if I take m going to 0 limit, this correction is not disappearing. See, unlike the examples that we saw earlier in QED, in QCD, the mass correction was such that when I took mass to be 0, the correction disappeared. For elementary scalar field, that is not so. Is that clear? So, if in this limit delta m square is not 0, So clearly m, we said that m is not a natural parameter. And a correction to the mass is proportional to lambda cutoff square, delta m squared. And if my theory is valid up to say 10 to the 16 GeV, then the mass of this scalar particle would be 10 to the GeV, radial to correction would be 10 to the 16 GeV square. So that's a huge number. And you said that they have done an exercise of two scalar fields. You've done a scalar. Okay, let me just present that. What does this mean? Okay, before that, let me make a remark about the coupling constant of this theory, and then we'll go back to this. Now, on this, on the other hand, there is another parameter we have, which is lambda here. The coupling constant, 4 scalar coupling constant. Now, lambda going to 0, is there a symmetry? Because lambda is the strength of the self interaction. So there is no interaction. So we have a free theory, and free theory is hard symmetry theory. So lambda is a natural parameter. But m is not. What does this coordinate divergence mean? So we have seen the source for any problem is of this kind of a problem is if there is a coordinate divergence in the theory. That's the technical source. Because then corrections turn out to be, for masses turn out to be proportional to that cutoff. Just for dimensional grounds. Mass square dimension, mass square dimension. What does that mean? Consider a scalar theory, a theory with two scalar fields. And we'll call them small phi and capital big phi. Described by Lagrangian density 1/2 d mu small phi square plus 1/2 d mu big phi square minus m square phi square. Mass for the smaller phi is m square, and mass for the capital phi square is capital M square, and then an interaction. Small phi square times I could put self interactions also, lambda small phi 4 and maybe some other coupling, but that's not interesting for my discussion, so I'm not putting that. Instead, I'm putting a coupling which mixes small phi and capital phi. And let me assume that m is much smaller than m. I could add that also, but that's not relevant for the discussion that I'm going to put. So let me not worry about that. You can complicate it that by adding that. There'll be some additional structure to it, but the physics of it is not going to change for what I'm doing. So what does it mean? So I have a theory of a light field and a heavy field. What light field and heavy field are talking to each other through interaction. And is this the exercise that was done? Huh? So this is the exercise. So let's revise what we had learned maybe there. You may have put 4 terms also, I don't know if you want. So this is what it is. Now if I want to calculate one loop mass corrections to these parameters, m, small m and capital M, what would it be for small m? It would be given by a diagram. External x is small phi, and from this coupling I would have a loop this is loop of capital phi. Dashed is capital phi, dot is small phi. Dash is heavy field, small dot is small field. Now what would that be? And this coupling is G. So G times d for k of this propagator, k square minus m square. Is that what it is? And now, if I use dimensional regularization, what would be the answer here? This is a quarterly divergent integral, and let me evaluate it by dimensional regularization. G square is as it is. It would be proportional to this mass times log mass square. Now, by simple dimensional regularization. I throw away 1 by epsilon pole, and this is what will be there. Similarly, if I do this now, this is capital phi, this is small phi, this is g, so this will be g square d for k square minus m square, and by dimensional regularization will be g square m square log m square. So therefore, m square at one loop would be m square at 3 level plus g square m square log m square, and m square at one loop would be m square at 3 level plus g square m square log m square. Because log m square times that mu square normalization scheme, I'm not keeping that. There's always dimensional regularization introduce that mu square. I'm not keeping track of that. Let me put that also. So the log is dimensionless because you define log for dimensionless object. Now from here it's very clear what you have is that the large mass is picking a term proportional to small mass. So that is small. But small mass is picking up a correction which is proportional to the large mass. Unless g square is very small, this can be larger than this. Now, if the difference of the two mass scales is this is 100 square and this is 10 to the 16 GeV square, and the couplings typically are order 1 or 1 by 100, 1 by 10, G square is. This correction is huge, and this correction will destabilize the small value for this light mass. And now this is precisely what it is. Is essentially what it tells us from this point of view, when we had one scalar field, this cutoff essentially is the whatever highest mass you have in your theory. In this theory, the highest mass is the capital M. This theory is supposed to be valid up to capital M. So the light mass is picking up a correction which is proportional to capital M. So that's what here, sometimes you present it like this and sometimes you present that like that. What do you mean by presence of Corey divergence? Corey divergence means that this is essentially the highest value of the highest physical mass of the theory. So you put that highest mass here, which is capital M for that theory. Highest mass with which this theory is interacting. Here was this light mass theory of small phi, and it is interacting through this coupling to the highest mass theory characterized by capital M. So therefore, the light mass theory, the mass of the light mass sector gets driven to the highest mass. Now in any theory, this is an example, is any particle experiences gravitational interaction. So the highest mass scale in nature is 10 to the 19 GeV. So the gravitational effects, if I were to include here, that will put me 10 to the 19 GeV square here. So that tells me an elementary scale fields cannot be light of 100 GeV, they cannot be even 1 TeV, they cannot be 100 TeV. The only natural value from them is 10 to the 19 GeV square, because then only their corrections will be proportional to themselves. Is it clear? I mean, that way of thinking and this way of thinking are equivalent. What it means is that, this way of thinking means is that if there is any physics that is coupled to this theory, which is of higher scale, that is why this correction will be controlled by that scale. An explicit example is here, is that we have a light theory coupled to a heavy theory through this interaction, and therefore the light mass correction is proportional to the heavy mass. So I'll just make last statement and then stop today. So now this we discussed it as an example of two scalar fields coupled here. Now this need not be a heavy field, need not be a scalar field. Heavy field could be a heavy fermion. Any other heavy field, or it could be simply a new interaction, like the interactions of grand unified theory, which is 10 to the 16, or new interaction that is quantum gravity. All of them will result into a behavior of this kind for the light mass. So radiative corrections destabilize, radiative corrections destabilize the small masses of elementary scalar fields, because they pick up corrections due to corrections proportional the largest mass scale interacting with the light scalars. Of course, if we take the point of view is that there is no physics of this kind, which means if I have elementary, for example, standard model physics, I have elementary scalar field of 100 GeV mass. And if I say that there is no physics beyond 100, there is no mass of particle beyond 100 or 10 times 100, because this is also suppressed by G times coupling constant, right? G square times M square. So G square may be a factor of 100. So 10 times 100 GeV. If I say there is no physics beyond that, then I don't have the problem. Because there will be no capital M scale anywhere. There is no grand unification. But I have to face the problem of one mass scale which is larger than that, we know, and that is the mass scale of gravity. So I can take the point of view maybe mass scale of gravity is not a fundamental scale. It's a very, very important observation. If I take the point of view the scale of quantum gravity, which normally we thought was fundamental, maybe it's not a fundamental scale. And if it's not a fundamental scale, then there's no such problem, because I will never but I have then to prove that effective four-dimensional gravity, which is governed by the Newton's constant, that scale is not fundamental, but effectively that gets generated through effective scale, which is only 1000 GeV, 10 times Higgs mass. Then I have to pick up a method of doing that, right? And that is this physics of extra dimensions. So we'll talk about that, maybe these things next time.